Good morning, mathematicians. I tricked you all. You thought office hours wasn't happening today. But you were wrong. You were wrong to doubt me. And yeah, that's all I have. I hope you'll all repent. Probably gonna keep it short today, because as you can see, I'm in a new location, super top secret math location, where I'm doing very serious math work with my good friend in the background, who's currently working on some applied math, applications of vector lattices to cooking breakfast, is what he's working on. Good morning, Kostaka Corey and Sergio Polar Bear. Hope y'all are doing well. I don't know what we'll yap about today. Maybe we go back to the L functions paper. Maybe let's have a quick look at archive. See if there's any juicy new drops in the last couple days. Yeah. What else is there to say this morning? What have I been working on? Well, as you saw, there's some new interviews coming down the pipeline. And I've been thinking more about the future of this channel, you know, what episode should look like. There's an interesting point that was brought up by my interview guest, who that episode will be dropping in December. You know, he raised some doubts about the actual effectiveness of math education on YouTube, and the sort of, like, what was the word he used? Entertainment, edutainment, you know? And I pushed back a little bit, trying to argue that there was, you know, that I do think things like 3 blue, 1 brown offer conceptual value. But I was reflecting on it, you know, and I was thinking the videos that I put out, say, about the categories of modules series, where I, wow, all these group theory articles look really interesting. Another article on the number of homomorphisms. Wow, that's great. Yeah. What was I saying, though? Anyways, I think maybe the content that's more valuable is ones where I focus less on the gritty details of proof, because, you know, that's kind of boring. And I just give you, I focus more on explaining the intuition behind things and doing examples and whatnot. I don't know what you guys think, but maybe that's what I'll try to focus on more. And hey, it's kind of easier on my end too. So I think it might be easier and more useful. I don't know. Wow, this is there's such cool papers here. I see like 4 papers right away that I kind of want to read. Yeah, let's take a look at these. These look good. Also, here's a funny anecdote from my supervisor. So apparently, so my supervisor studied under the famous Jim Arthur, and apparently he submitted his thesis and he wrote every chapter. You can do the proof as an exercise. Wait, which proof? Oh yes, the proofs in the video. Yes, exactly. I should fully embrace the mathematician educator in me and just give every proof as an exercise to the reader. I think that's ideal. But yeah, so my supervisor, apparently in the first draft of his thesis that he sent, he had written every chapter with different different flavored terminology. So like chapter 1 was all like agricultural like verbs and stuff, and then in chapter 2 was all like militaristic verbs, like we'll attack the problem and like flank it, blah blah blah. And which I think is amazing. I'm like, why do we have to be so boring? It's not like that writing style is somehow so distracting from the the content of math. It's just a deliberate choice of words, and in my mind, that's like a very artistic way to express our craft. And anyways, his supervisor actually tracked him down. He had submitted it that day and then was at a party, and somehow his supervisor tracked him down to the party and called him and was like, no, like, you need to fix this. And then I was like, oh, well, does that mean you're going to let me write my thesis like that? And he said, absolutely not. But I mean, come on, that's terrible. That's boring. I feel like physicists have more fun. You see some of these physics papers on Archive, and they've got just these ridiculous, silly titles. I want that for us. Okay, sorry, Rod. I know I saw your message here a couple of minutes ago, but you don't think one can learn math principally from YouTube? Yes, that's true. It is too passive. Yes. Yeah, you're right. And yeah, that doesn't mean it doesn't have any value. Yeah. Because definitely, I mean, I think the two things that it can do is, one, it can expose you to new ideas that you wouldn't have seen before. You just see someone, even if it's just like a lecture from the Fields Institute or something, and you see some topic pop up and you're like, whoa, that looks interesting. And you click on it and then it's like, whoa. Or, the stage that I'm at in my life where I've started finding value with lectures on YouTube is there's some papers that I'm interested in. And then sometimes now I can find videos of the authors giving talks about their papers. And in those talks, they're able to express more some of the ideas and how I should be thinking about things, because some of these are like long technical papers that are very complicated. Yeah. Okay, let's have a look at some of these group theory papers here. This looks interesting. Finite simple groups have many classes of prime order elements. Let T be a finite non-abelian simple group. Giudici, Morgan and Prager have shown that the order of T is bounded above by a function depending on the maximum number of automorphism classes of elements of prime power order. Interesting. In this note, we strengthen the result by showing in particular that prime power can be replaced by prime. Oh. Okie dokie. That seems kind of cool. Okay, let's just read all the abstracts first, and then we'll figure out which one we want to sink our teeth a bit deeper into. Mind you, maybe I should end stream as soon as breakfast is ready. And breakfast is ready. Okay. Yeah, okay. Unless you guys want to see me eat omelets on stream, we could do a mathematical mukbang. That'd be good. It is currying. I had curry last night. You read about the tensor Ham adjunction, and it sounds exactly like... Oh, wait, really? Tensor Ham is currying? I guess it works the same way. Yeah, I guess it basically is the same proof. You think Real called it exactly that in a talk you just watched yesterday? Huh. Well, there we go. Yeah, I guess it makes sense. I never... As obvious as it is, somehow I never made the connection. But yeah, I guess it literally is like the same proof. Another article. Yeah, this is the greatest name for an article I've seen for a long time. We extend the class of abelian groups for which a conjecture of Asai and Yoshida on the number of crossed homomorphisms holds. We also prove a general result which connects certain problems concerning divisibility in groups to the Asai-Yoshida conjecture. One of the consequences is that for finite groups F and G, the number of ordinary Homs is divisible by this. Yeah, okay. If F over F prime is a product of a cyclic group and a group with cube-free exponent, occurring in the categorical interpretation of lambda calculus in CCCs. CCCs? Qu'est-ce que c'est? Following two theorems due to Frobenius, Gigatrad, and Solomon may serve as a good illustration. Wait, Frobenius 95? What? Surely this means like 1895, right? Hang on, let's go see. Fro 95. What's that citation? Yeah. Wow. Yeah, I guess we're at the point where you have to pause and the last two digits, and you got to start thinking. It's gonna start getting worse, right? Because like, okay, I mean, how often do people cite results from the 20s? Like, not that often. But as we get further up into the 2000s, there's gonna be a lot more crossover. So what do we have here? In any group, the number of solutions to a system of coefficient-free equations, I don't even know what that means, is divisible by the order of the group, provided the number of equations is less than the number of unknowns. Okay. And the number of homomorphisms from a finite abelian group to a finite group is divisible by GCD of these two things. So these guys resolve the conjecture? Interesting. And cross homomorphism. So there's some group cohomology going on up in this thing? You know, it's an interesting question that I've been meaning to do a deep dive on. So maybe we should do it maybe tomorrow, or maybe when I get back to Calgary, we'll have a nice long episode. I'm sure I've yapped about this on stream before, but let me bring up my my writing tools. So basically, the idea is just asking about iterated orders of iterated automorphism groups of groups. So, well, some of you know I have a short about the fact that the automorphisms, if n is not equal to 6, 2 or 6, then the automorphism group of Sn is just Sn, right? So, well, actually, let me define some notation here. So let me call A0, A0 of G will just be defined to be G, and let's define A1 of G, let's define AN of G to be the automorphism group of AN-1 of G for all n bigger than or equal to 1, right? So you're just taking, you start with a group, you take its automorphism group, you take the automorphism group of that, you take the automorphism group of that. And so we see that, for example, for a group like S3, we just get this repeating is just S3 ... for forever, right? But for a group like the cyclic group of order 2, its automorphism group is trivial, right? So it goes like this. So I think about these are kind of like akin to like rational numbers, right? If you think about it, because it's like you have this infinite sequence and eventually it's repeating, right? But now the question is, are there does this sequence always converge. So yeah, there's a number of questions you can ask. Like, given a group, does the sequence eventually, like, does it end in a tail of zeros? Or does it end up on a repeating sequence like this? And something that's maybe like, I don't know if it's an open question or not. I found very little resources talking about this. I found like one paper once where people talk about somehow bounding degrees of automorphism groups in terms of the base group. But then the other question you can ask is, well, are there any irrational groups? By which I mean, you look at the sequence A0G, A1G, A2G, and are there any groups for which there's no up to isomorphism, there's no repeating pattern? And I think this is a very interesting question, and I have no idea how to approach it. But I think it's very interesting. Or like, yeah. So the obvious way, or maybe not obvious way, but one way to attack it would be to try and say, get some heuristics on, like, if you can try and come up with a group where you can always force it so that the order of AN is strictly larger than the order of AN minus 1, then, well, yeah. So this would be like you could call this like a divergent group or something, maybe. This reminds you of a remark that you read about periodicity of homotopy groups, that sometimes for finite complexes, the atom spectral sequence becomes periodic for conceptually the same finiteness reason. I am not sure I understand that remark at all. Periodicity of homotopy groups. If you can define an algorithm which computes aught G in some bounded finite space, then the sequence must repeat. Whoa, what? If I can define an algorithm which computes aught G in some bounded finite space. Oh, I see. Interesting. So maybe that would be a strategy to prove, like, that for all finite groups, it eventually becomes periodic or something. And then that's another interesting, because now we, like, okay, I think this is a hard enough question already for finite groups, but now consider infinite groups, like, take the automorphisms, right? The automorphisms of the integers is just the cyclic group of order 2. So even though you start with an infinite group, quickly the sequence dies, right? But of course, in general, I would expect that, like, you can cook up some pretty wild infinite groups that just, like, it explodes off to infinity quickly. I'm confident for infinite groups we can cook up examples that explode quickly. If the algorithm uses finite memory, then by the pigeonhole principle it must repeat. Interesting. Okay, I'm kind of tempted to look up some of these results now, but I do want to look at let's at least take a look at the abstracts of these other interesting papers. We survey the known group properties that a sequence of finite groups or group actions needs to satisfy to admit subsets. Hang on a second, I lost myself. Known properties that a sequence of finite groups or group actions need to satisfy to admit subsets of bounded cardinality producing expander Cayley or Schreier graphs. I don't know what a Schreier graph is. We produce an infinite amenable group and solvable groups of bounded derived length do not produce expander Schreier graphs, generalizing with easier proofs results of Lubotsky and Weiss for Cayley graphs. In particular, the poor expansion properties of a group action in general cannot in general be detected by looking at the abelian sections or at the representations above the stabilizer point. Representations, in the sense of representation theory? Oh, baby, now I'm excited. What's going on? Expander graphs are sequences of finite graphs that are at the same time sparse and highly connected, and play a basic role in various areas of mathematics, computer science. Yeah, I want to get what's going on in this paper here. Yeah, shout out, by the way, to the Ramanujan conjecture, which depends on the proof of which depends on the Weil conjectures, and all of this goes into providing the first examples of expander graphs. You gotta love that interdisciplinary math going on. Wow, this paper is only 11 pages. I could read it. Whoa, Rep G. Okay, what's going on? Whoa. Okay, this is very cool. What is going on here? Let Rep Kg denote the number of irreducible complex representations of G of degree at most K. If G can be generated by D elements, then the two functions, okay, we don't know what ab K is, are connected by these inequalities. What the hell? I'm so intrigued. What is this? Okay. Ab K is the function, it's the soup of the relative cosets. It's the soup of the coset of wait, so H prime is fixed? What is going on? What are we trying to... G prime is the commutator subgroup of H. I see. So we're taking the soup over all subgroups whose index is at most K of the... Yeah, live rep theorist reaction, yeah. Rep theorist unboxing videos. Yeah. I saw in my suggestions the other day, I saw a PhD thesis unboxing video. I was like, what? I guess she was just like, I didn't even click on the video. I like hovered my mouse over the thumbnail, but I guess, she got like a printed version of her thesis and unboxed it, I guess. I don't know. Will you guys watch that? I have no idea what you guys will watch. The other day I made some offhanded reaction video to a Reddit post, and that one's blowing up. So there's no predicting. There's no pleasing you guys. Okay, I may actually take a deeper look at this paper later on my own. This is really interesting. I wanna think more about finite groups and representation theory. Open problems. Ooh, yeah, you gotta love it when a paper has an open problem section. Let's look at this. Question 1.1 highlights the lack of tools preventing expansion. Live stream my defense. I mean, it is open to the public. So, and I did come across a channel the other day that, just uploads videos of people's PhD defense. Hello, Ownage Effects. But what I found really annoying about that channel is they just put so-and-so's name and they don't tell you what the subject is, which is very annoying. I guess they're mostly doing it for people to have like a copy of their defense online. But me as a random viewer, I'm like, well, I want to, click on, I don't know, maybe if I click on random videos, if I play defense roulette, maybe I'll learn something interesting about like municipal infrastructure, PhD thesis. I don't know. You like more in-depth mathy videos? Okay, well, good to know. My background changed. Yes, indeed. Yes, indeed. I'm traveling. I'm on vacation in the sunny beaches of Edmonton. You know, sunbathing and all of that good stuff. Um, yeah. Anywho, I'm probably gonna wrap stream up pretty soon. Like I said, I'm gonna keep this one short. Tomorrow morning will probably be short as well. We'll see. Probably be short as well because I need to hit the beaches of Edmonton. Take a dip in the sun-bathed river here. But Monday maybe Monday we can have a longer stream. Let P be a prime and let GP be the direct product of P copies of PSL2P is the sequence and expanding sequence of groups. This is very cool. 100%. Let me, beaches in November? Yeah, don't you know Edmonton is, look up Edmonton. Perpetually sunny. Crazy moose behavior, yeah. I mean, as long as it's above minus 20 Celsius, you can go swimming, right? Okay, let me actually save this paper to my desktop because I do want to know more. What's it called? Groups that produce expander graphs by Sabatini. Groups that produce expander graphs. Sabatini. Oh, another PDF saved to the desktop. Who knows if I will ever read it that in depth. Can I tell you what I'm reading? It's a recent archive preprint looking at families of groups where if you take their Cayley graphs, those Cayley graphs produce what are called expander graphs. Basically, you look at the Laplacian... expander graphs, there's some sort of measurement of how connected a graph is, and expander graphs have like good connection properties. Basically, it's not the traditional measurement of connectivity of a graph, but there's different ways to measure connectivity. And then what's interesting about it, though, is that there's a way that you can capture this in terms of the eigenvalues of the Laplacian matrix, and then there's like cool analysis to be done there. Was Gordon Lightfoot from Edmonton? I don't know. He's been blowing up on TikTok lately, right? I feel like I've been getting a lot of YouTube shorts about the Edmund Fitzgerald, because it was like the anniversary of that happening recently or something. Yeah. Okay, let's look at this last paper, and then we're going to say bye-bye. We will say bye-bye. Endomorphism and automorphism graphs? I am intrigued. I have no idea what that means. Let G be a group. The directed automorphism graph of G is a directed graph with vertex set G, and there's a directed edge from vertex A to vertex B if A is not equal to B, and there exists an endomorphism mapping A to B. Wow. I'm intrigued. Also, I'm very intrigued. You know, I love asking questions about doing things in repetition or cyclically. So you could ask this with Cayley graphs as well. But now imagine this question where you start with a graph, and then you take the automorphism group of that graph, and then you take whatever this graph is that they call it, the edge, the oriented endomorphism graph of this thing. And because I don't like oriented stuff that much, let's say you look at the underlying graph, and now you take the automorphism group of that. And you cycle back and forth. And now we can ask the same questions, right? We can ask interesting questions. I feel like, does this converge? Do the graphs blow up? Are there any like irrational sequences? Can I give you some advice if you want to get into homology and cohomology? Yeah, watch all my videos about homology and cohomology. I'm only half kidding. Tell you the preliminary stuff that you need to know. Well, yeah. So do you mean, are you talking about the topological forms of the theory, or just like purely like algebraic, like homological algebra? I mean, I recommend to everybody. Oh, did my stylus just die? I recommend to everybody, a Luffy, for all your undergrad and early graduate algebra needs. Not all, but most of them. So, go crack open a Luffy, jump over to the chapter on homological algebra and start reading. As soon as you get confused and find terms whose definition you don't know, the beautiful thing about this massive tome of a textbook is you can just flip back to those sections. But I mean, roughly speaking, what do you need? What should you do before getting into homological algebra? You should, have a decent grasp on basic linear algebra. Have a decent grasp on like groups, rings, and modules. I mean that's pretty much it. That's what the prerequisites are. Yeah, if you're talking about more in the topological sense, like if you want to learn de Rham cohomology, then you should probably know some differential geometry first. But for example, like you can do, I don't know. But if you want to get into group cohomology, I've got some videos on that. What university do I recommend if you want to study group theory in grad school? No idea. I have no idea what universities are strong in group theory. You'll have to use Google or AI for that one. I don't know, unfortunately. Can I suggest a book to learn basic commutative algebra? Well, I just wrote down a Luffy. So there you go. You already have a course on algebra until module theory. Okay, well then, I would still go read a Luffy. But it depends on what you want to do, right? Like if you are aiming towards algebraic geometry in the longer time, the classic references are Atiyah McDonald and Eisenbud's commutative algebra. So if you want to aim more for that, I would go there. Otherwise, go check out a Luffy, go learn more about that, classification of modules over a PID, something like that. Since we're asking for Rex, any suggestion for a book on homotopy theory? No, I don't know a ton about homotopy theory, unfortunately, to be honest. I don't know. All I can recommend to you is just any of the standard, recommendations for basic algebraic topology. Hatcher's book, May, Tom Deek. Yeah. Anywho, I think we're gonna end it there. So thanks everyone for joining me today.